The alcohols and halogen alkanes, we did the first 25 questions. Organic chemistry, both in unit 1 and unit 2 are important. Like a weightage is very high. So it's important that you understand each part. So some organic molecules, either on their own or a part of a mixture, contribute to some very unpleasant smells, odors. The molecule shown below is commonly, which is called isovaleric acid, is responsible for a smell of sweaty feet. So this compound can be used to produce ester that have important industrial uses in a pharmaceutical industries as a sedatives or tranquilizers in a food industry as a flavoring or the fragrance additives. The molecule with this systematic name 5-alpha and andros 16-ene-3 on label X in this question was found in a human sweat and a urine. However, in other situations, these molecules can induce a very different effect. For example, X is present in commercial products used by pig farms to determine how so are ready for mating. Then, what is the systematic name? So what is the systematic name of this isovaleric acid? So we have to state the systematic name of this compound. So when you check the groups which are present here, and the answer is actually there in the question itself. As you can see, the beginning of this, like there is C double bonded with a ketone group is there in this compound. And so first, how many carbon atoms are there? Systematic name or IOPIC name? The standard name in which we count the carbon atoms and we name according to a functional group. So here 1, 2, 3, 4 carbon are there in the straight chain. So 4 carbon in a straight chain and this is a branch. So when we number the carbon, this is 1, 2, 3, 4. So third position, we have a carbon chain. So it is 3-methyl. And then 1, 2, 3, 4 are there. So it will be but. Single bond N. And it will be oic acid. So this is 3-methyl butanoic acid. So this compound, systematic name of isovaleric acid, that is the 3-methyl butanoic acid. What is the molecular formula of isovaleric acid? So molecular formula, for the molecular formula, you have, this is a skeletal formula is given. You just have to identify because this will be, one bond is there. So this will be CH3, 3 bonds, CH. This will be CH3. This will be CH2 and 4 bonds are there. So C. So 1, 2, 3, 4, 5 carbon. So C5, 3, 6, 9, 10 and O2. So C5, H10 will be there and then O2 will be there. That is a molecular formula. Then isovaleric acid has 3 structural isomers which are also carboxylic acid. You have to draw the skeletal formula. Like we have to just make the 3 structures of the isovaleric acid. So we can make the branches like here we have 1, 2, 3, 4, 5 carbons. So 1, 2, 3. Like if you start with this one, OH, this is there. These are the carboxylic. So 1, 2, 3. 4, and then we can make a branch. Or another one, because it's a skeletal formula, so we are not supposed to write the carbon here. So this is OH. So 1, 2, and then we can make two branches, one up and 1, 2, because 1, 2, 3, 4, 5 we need, 1, 2, 3, 4, 5, and 1, 2, 3, 4, 5. So all of them have the 5 carbon, like this is 1 carbon, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, and 5. So 5 carbon atoms are there. So these are the isomers of isovaleric acid or valeric acid. Then at room temperature, valeric acid is a liquid. It is sparingly soluble in water but very soluble in ethanol. Describe a simple experiment you would carry out to show the different solubilities of valeric acid in these two solvents. No measurements are required, but you should state how you make your experiment valid. State an expected observation from your experiments. So how we can identify the solubility? So first we'll take equal amount of the two solvents or equal volume of the two solvents, and we'll add the same amount of or equal volume of valeric acid is there, and we shake them. If it is complete like sparingly soluble, partially soluble in water, so it will create two layers. But if it is completely soluble in readily soluble in ethanol, so there will be a single layer. So a simple, without any calculation, how we can demonstrate? So we'll take equal amount of equal volume of water and ethanol. Then we will add equal volume of valeric acid because two liquids are there. And we will shake. And then with water, because it is sparingly soluble, it will form two layers. That is what we'll observe. But in ethanol, with ethanol, it will form a single layer. That's how we can identify. This is a simple test to show that it is soluble. Then we have isoamyl alcohol is alcohol from which a valeric acid can be produced directly. This alcohol form intermolecular hydrogen bond. Use a simplified representation of alcohol ROH, how hydrogen bonds can be formed between two alcohol molecules clearly indicate the bond angle and the hydrogen involved in the bonding. So we have to show hydrogen bond angle is always 180 and the lone pair. So how we can represent, like example, if we have R means like a carbon chain, alkyl group, then there's a lone pair and there's hydrogen. Then we have this. This is because this is a bend or a V shape. That's why I drew it this manner. There will be a partial negative here and a partial positive, partial negative, partial positive, and there will be attraction between them, and the bond angle will be 180 degrees. That's how we draw. There are London forces between the molecule of isoamyl alcohol. How London forces are formed? This is a static question, means the structure of answer is having importance. So how London forces are produced? Because due to instant dipoles, the distribution of electron, like temporary asymmetry of electron distribution, induce the charge or the dipole on an adjacent molecule. The temporary unequal division or distribution of charge on one molecule induce charges on adjacent molecule. So when the adjacent molecule get a charge due to unequal distribution, as a result, we'll have a London dispersion. So this is a fixed answer you have to learn. The straight chain structural isomer has a boiling point of 138, suggests whether the boiling temperature of isoamyl alcohol will be higher, lower, as from a straight chain. Straight chain compounds, they have a large surface area. If they have a large surface area, the attraction will be more. So the boiling temperature for a straight chain will be higher. Why it will be higher? Because the branches, when we have like isoamyl alcohol is there, the branch, it will have branches. As a result, the branch will reduce the surface area or weaken the van der Waals forces. So straight chain compounds have high boiling point. That is one thing. And the branches reduce the surface area. And when it reduces the surface area, what will happen? It weaken the attraction. So a small amount of energy can separate the molecule, so the boiling point will decrease. In part G, the oxidation of an alcohol of this type with acidified sodium dichromate could involve either reflux or distillation. Explain why either could be used in this case. Molecule X, the molecule identifies X is introduced to question 23 can be from alcohol Y. Like here, this molecule X in the beginning of the question, which is turned into a ketone, it can be formed this from this alcohol Y. And they're saying why we can use both reflux condenser or the simple distillation as well. Distillation, why both? Because this is a secondary alcohol. Secondary alcohol can oxidize to ketone. There is no intermediate, because like this carbon which is forming a bond with OH has two carbon chains around. So this is a second degree or a secondary alcohol. So because it is a secondary alcohol, the compound is a secondary alcohol. And if it's a secondary alcohol can only be oxidized to ketone. So it is irrespective of what we use a reflux or a distillation, the product will remain same. An alternative reagent for oxidation of alcohol can be potassium manganate. However, this is likely to produce other product because X contain another functional group. Potassium manganate, when alkene is there, if they use potassium manganate acidified, it will break down this double bond to single bond and it will produce a diol, like the two OH group will be attached. So if for a compound X, basically this compound. So for a compound X, even compound X, there's a double bond. If you use acidified potassium manganate 7, this will form a diol. Why it will form a diol? Because there is a carbon-carbon double bond. So functional group that it will react, that is carbon-carbon double bond or alkene, and type of the molecule it will form a diol. So acidified potassium manganate 7 will form diol if it is reacted with acid, if there is a double bond. So this was the assignment related to alcohols and halogen alkanes.